Hi, I'm Devin Bost from the data engineering team at Overstock, and I'm going to be talking about Apache Pulsar implementation patterns and best practices. We'll start by talking about the mindset of streaming. It's important to develop a streaming mindset to get the most value from a stream-based architecture such as Apache Pulsar. After that, we'll talk about patterns, and then we'll get into some code. As part of developing a streaming mindset, I'll talk about some of the challenges presented with microservice architectures, because stream processing changes the way we do things and can solve many of the problems that occur with microservices. Now, I'm not saying microservices are the enemy, but they're not the end-all be-all either. So, in a 2018 systematic review that reviewed quite a few papers, several pain points were identified. The top three categories of pain points associated with microservices were architectural, storage-related, and management-related. The greatest architectural pain was the complexity of applications driven by microservices. And complexities were magnified around subjects like API versioning, dealing with service contracts, and coordinating communications among microservices. The greatest storage-related pains involved distributed transactions and data consistency. Challenges with distributed transactions and data consistency tend to appear most frequently at scale when dealing with large compute volumes or high-performance applications. The greatest management pain was operational complexity, and this can take many forms. So how does streaming with Apache Pulsar solve these problems? First of all, streaming with Pulsar allows you to break up applications into functional components to achieve better separation of concerns. It allows you to build a communication layer or fabric that behaves like its own storage layer, but specifically for communications between applications. You can think of it like a switchboard that allows you to easily connect applications together to connect data streams, either where you're making data available or where you're consuming data from others. A new application can simply identify data it wants to use from the fabric, plug into it, and you're off and running without anyone else needing to make code changes. Let's say, for example, you need to version your application in a way that breaks your data contract. At that point, it's simply a matter of creating another code path in the stream and switching over to the new components. In many cases, messages can be paused while components are reconnected or switched to an upgraded version without resulting in downtime. For real-time scenarios where messages can't be paused, although I won't go into these scenarios in detail in this presentation, I cover some patterns for dealing with these cases in the video from my presentation at the 2020 Apache conference. That was about a week ago. So once that recording is published, I'll include a link to it in my Pulsar YouTube video playlist. And a link to that playlist is mentioned at the very end of this presentation. So back to this analogy, applications can be plugged into this alternate form of power. This is especially useful if you simply want to consume an existing data stream to enrich your application. With each additional application that adds data to the fabric, new doors open for other applications. A world of possibilities emerges as more and more applications produce data to the fabric. Data from multiple applications can be combined, pre-computed, and then cached for real-time lookups. We can also pre-process the data in other ways and share the output back to the fabric, so other applications can make use of it without needing to duplicate the same logic. Consequently, we obtain a framework of data that applications can build upon. This keeps applications consistent in a distributed way. For example, if two applications are consuming from the same data stream, they'll have the same data. By performing computation earlier in the process, you can provide actionable insights to downstream consumers. The more of that processing that can be done in advance and put back onto the communication fabric, the more doors open up for intelligent and higher level automation. As more developers consume data from the fabric, reduce that data into meaningful information, and put that information back into the fabric, other applications can be developed to perform these higher level tasks with this new information. Another benefit of stream-based architecture is clean separation of concerns. By keeping your code modular and bite-sized and simple, your code stays clean, organized, and easier to maintain. The modular design of Pulsar-based architecture makes it easier to plug and play components and parallelize development efforts as a team. For example, by starting with architectural diagrams, it's easy to break up a large or complex flow into bite-sized components that developers can develop in parallel. We've seen this work quite effectively for our projects at Overstock. So consequently, it becomes easier to plug multiple data sources into a single application. The data contracts form the seams between applications, and when something needs to be changed, it's easy to swap components out without downtime. Teams can start, like I mentioned, from an architectural diagram of a flow, and in parallel can bridge components together through these data contracts, which greatly improves productivity. And when something needs to be changed, by leveraging the data contract, it's very easy to see what needs to be done. The data from one system can be used to power many other applications, so the reusability becomes synergistic. These data streams become streaming assets for your team and for the company, as well as for your customers. This approach allows us to focus more on the bigger picture and think about how our components fit into the larger ecosystem of applications. It gets us thinking more about flows and how our data will affect and be used by others. There's one other major problem with microservice architecture: silos. Most microservices are designed to own their own storage. This can be a good thing. However, this practice can also result in data that is created in a vacuum, that is not designed for use by other applications. Microservice applications tend to behave like black boxes, where you've got an input and an output. But if you need information that wasn't explicitly expressed, you are out of luck. Using shared storage doesn't necessarily eliminate the silos either. Just because data is put in the same place doesn't mean it integrates well or is usable by other applications. Shared storage also introduces its own risks, such as limited flexibility and increased risk of failures. It's actually a pretty common problem for teams to overuse a particular storage technology or type of database, and that can cause many other types of problems. So streaming opens up the process. It forces application interoperability by requiring communication to happen between these small functional components through data contracts exchanged on the fabric. So applications on the fabric get designed in a way that encourages cooperation. These connections form vast highways of data that become like a storage layer, a layer for real-time information. Streaming liberates your architecture and decouples your storage. If you decide you want to pump your data into different storage technology, for example, you often don't even need to make code changes. There are tons of connectors that Pulsar has made available out of the box, and if you have a new use case for storage technology that isn't mentioned here or on the, well, I guess the better source is the Pulsar official documentation, then you can easily write your own connector. And we've done this with a number of data sources at Overstock. This approach also allows you to easily transform your data to optimize its use for different types of analytics. And so, for example, that makes it easier to build BI dashboards. You could easily pump that data into something like Elasticsearch or Apache Druid to enable real-time business intelligence. It also reduces the barrier to machine learning, since real-time data can be easily curated for ML features. And this concept of curating data for machine learning features and to support data analysis, that was a primary focus of the talk that I gave at the Apache conference. So if you're interested in that or in machine learning, be sure to check that video out. So to wrap up from this section, let's cover just a few more thoughts on developing a streaming mindset. When thinking about message flows, find ways to break up a process into steps, like an assembly line. Think about how you can prepare your messages to be most useful to others. If that requires a lot of transformation, consider breaking it up into multiple functions or producer-consumer containers. Now in this case, the kid in the picture has the right idea. He's just using the wrong technology. Message flows are push-based, so it's important to keep that in mind. You always want to be mindful of how data you produce might be consumed. More data is almost always better because it can be easily filtered down by other components before it reaches the final consumer. If you can provide more context, it's better to include that and allow the pipeline to filter out what they don't need downstream. Now let's talk about patterns. So at a high level, we'll talk about some of these basic messaging patterns that you can implement with Pulsar. The filter is one of the most basic patterns. You can filter by removing messages you don't care about, such as filtering out bot traffic, filtering the specific user actions, or filtering specific clicks, etc. Another pattern is a transformation. Transformations are a very broad topic, and there are tons of transformation patterns, and entire books have been written about them. Many of the most useful transformations are intended just to make other operations easier. Enrichment is also extremely useful. Enrichment is when you enrich your incoming message with data from a lookup to data storage. It usually takes the form of adding additional properties to your message. This can happen in real time or near real time, depending on the storage technology or service that you're accessing. And so you could query an API or web service as your enrichment step to give you more context or perform ML inferences, etc. You can also go the other direction and populate storage from your flow. And this is also super common. And that storage can be any of the many types that Pulsar supports out of the box. Or you can add your custom connector like I mentioned already. Components can be chained together by having each component subscribed to the output topic of the preceding component. And when I say component, I say that generally to refer to either a Pulsar function or a producer-consumer application running inside a Docker container. So this is where we should be thinking from the assembly line perspective, where we're chaining together simple operations to perform a more complex overall task. If the components are built in a way that allows their behavior to be varied through configuration changes, then entirely new flows can be built without ever making code changes. This is easiest when done with Pulsar functions, but it can be done with containers as well. Some of the strategies for how to vary that behavior through configurations I won't really get into in this presentation, but if you would like more information, I'd be happy to give some examples if you just reach out to me. Now it can be more effective to filter before performing enrichment to reduce the number of reads hitting your data source. However, if multiple consumers need that enriched data for different purposes, enriching it in one place can reduce code duplication and complexity, since filters are simpler to write and maintain than enrichment functions. If you know in advance how to segment out your data, you can simplify the pipe even further by switching on incoming data with a router pattern. If the router is designed to be general enough, then new routers can be created simply by changing configurations, eliminating the need to make code changes to add new functionality and support new use cases. So, for example, like the router in the function config, you could simply specify what the output topics are that you're sending messages to, and you can include the message parameter or message property that you're using to switch on. So you could say, well, if the message property has particular value, then send it to this topic, otherwise send it to this other topic. Or you could have more complex logic. You could check a value. If the value is greater than a certain number, send it here. If it's not, then send it here. And so those are just some examples of ways that you could vary the behavior through function configs. A less common scenario but still useful is the merge. Again, you can specify those topics in the function config. And just really quickly about enrichment, you can easily vary your behavior through the function config by, for example, specifying exactly what you're going to be getting from your data source, or you can kind of use your imagination to think about ways that you could vary your behavior. But the best way to do that is if you have, let's say, 10 different data sources that you need to enrich from, just look for patterns across those implementations and see if there are ways that you can generalize, so you can reduce code duplication. So back to the merge. The merge can be useful when you want to consolidate operations, such as saving data to log storage. Or if you have a function here downstream from the merge that's general enough that it can process different types of data, and you're doing the same thing with it, then that's another good scenario for using a merge. A more complex kind of operation is one involving a keyed window, such as a time interval of 30 seconds, or it could be the messages for a particular user session, where that session duration is dynamic. And using this approach allows us to perform complex event processing over the window. A very, very simple example of this kind of event processing would be computing a sum over the window. So that could be like counting operation, or counting transaction dollars per user within a certain period of time. It's also possible to join over a keyed window. This allows joining across topics in near real time, avoiding the need to first save the data in a database or perform the join in a batch ETL operation. But generally speaking, it's a lot more common to do this kind of joining through stream enrichment, and I'll talk about that more. I talk about it more in my Apache conference talk. Since window-based operations require adding a stream processing engine, such as Apache Flink, to the Pulsar fabric, I won't go into more detail on these types of patterns in this talk. However, if you have use cases where you could benefit from this capability, please let me know, and let's talk about your use case so we can help you. Another common pattern is to transform your data prior to storage. In this case, we can use a transformation to pull key information into a wrapper, a message wrapper, or an envelope that we can switch on to decide how we want to store this data. So this pattern could allow us to, for example, reuse a single sink to store data from multiple data flows, even if each message has different storage requirements. And so you can see, like in this case, there's a particular structure, and so as the messages are coming in, we need to store them differently. And so by pulling data out through this transformation, we can make that easier to implement downstream. Like, for example, let's say in these messages that are coming in, what happens if they each need a particular message value, but the property names are different, but they mean the same thing? So in the transformations, you can specify, okay, well in this, for this flow, this particular property maps to this other one, and then you could do the same thing for these other two. And those are things that you can vary in the function config, so you don't have to rewrite your code. And then you can just pump them all the way down through. Although in that case that I just described, you'd probably want the transformations to happen before the merge. So just to give you some additional ideas here. Now there are also deduplication strategies that can help in various situations. So like probabilistic deduplication, such as using a Bloom filter, can be used when you just want to filter out the bulk of duplicate messages, where it's okay for some duplicates to get through. So if it's acceptable to have some duplicates, this approach can be simple to implement and can be a good solution. And just be mindful that if you add parallelism, then you're going to have more duplicates get through, but still it's going to filter out the bulk of duplicates. Now, hard or exact deduplication requires an external data store and is a lot more expensive to maintain. Some of our tenants are using Apache Ignite for this, But if your application doesn't require extremely fast lookups, I'd recommend using a storage that's a little bit less hot, such as Cassandra. Um, you can also use a SQL database if you really want to, but just be mindful that it's going to put, these can be pretty expensive, can put a lot of load on your storage technology. Now, before we get too carried away, let's go over the different subscription modes available in Pulsar. The subscription mode is used by the Pulsar consumer and has various effects upon how messages flow to consumers. Some subscriptions are more restrictive than others. In exclusive mode, if a second consumer tries to connect to an existing subscription, an error occurs. Exclusive mode, a subscription can only have one consumer, and this is the most restrictive subscription mode available. In shared mode, messages are sent to consumers in a round-robin manner. This improves throughput as more messages can be processed on the consumer side in parallel. However, order is not guaranteed due to the possibility of a race occurring between consumers, such as during garbage collection. There's also a key shared mode that allows messages with the same key to go to the same consumer, but otherwise it behaves just like the shared mode. In the failover mode, if a consumer dies, subsequent messages will go over to the failover consumer. Then if the consumer dies before the message is acknowledged, the message will time out, which will trigger redelivery, and so it'll be sent by the subscription to the failover consumer. When using a dead letter topic, when a message fails to be consumed, such as if it's malformed and throws an exception, the message will get sent to the dead letter topic for subsequent processing. Meanwhile, other messages will continue being processed as normal. The retry letter topic is a newer feature that allows a controlled delay to be set before a message is reprocessed. If a message can't be reprocessed due to an error, it is sent to the retry, or if it can't be processed due to an error, it's sent to the retry topic. And then if it fails again, it'll be repeatedly sent back to the retry topic until the max redeliver count is used up. After that, it'll be sent to the dead letter topic. And then meanwhile, other messages that are healthy can continue to be processed. And that max redeliver count, we'll talk about where you set that in some of the code examples later in this presentation. With a fan-out pattern, if you want a message to be received by multiple consumers, each consumer needs its own subscription. After the message is produced, it's distributed to each subscription regardless of their subscription mode. Now let's talk about message order. Message order is preserved during delivery in most cases. Let's talk about some of the exceptions. If you have multiple consumers using a shared subscription mode, message ordering cannot be guaranteed because the messages are delivered in a round-robin fashion. This round-robin behavior also occurs if you have added parallelism to a Pulsar function, and it is for the same reason. If your messages are produced out of order, then Pulsar will keep them in that out-of-order ordering. So if your messages are produced out of order, fixing that requires connecting to a stream processing engine like Apache Flink and using a timestamp or other message value to reorder the messages within a window. So you could say, okay, well, for a window of 60 seconds, the messages as they come through, we'll reorder them based on a timestamp on the message, and then we can send those through. But again, you need a stream processing engine like Flink. Now, for many applications, we want the ability to grab your historical data on demand, if it's available. If it's not available, we can store it for you. It's easy to do that with Pulsar. But if you've stored it somewhere else, like in Oracle or SQL Server or some other place, we often want the ability to get your historical data. And I'm speaking from the perspective of those who are operating Pulsar and administering Pulsar. So this practice gives us a valve that we can open if we need all that data, such as to populate a cache for the first time. It's also useful if we need to put out a fire, like if there's some sort of emergency or disaster recovery where we need to bulk load that data into our, to populate downstream storage and anything else that would be consuming that data. So to illustrate how a backfill works, Let's say we're processing messages as normal when a code update to a producer-consumer causes a problem and starts losing messages. There are various ways this could happen, such as if messages are getting acknowledged before they should or aren't getting produced downstream. Now we can quickly update the producer-consumer, but we've already lost messages, resulting in a gap in our message flow. The backfill path allows an engineer to trigger the backfill and replay messages, filling the gap. One side effect is that duplicate messages will be sent downstream. It's possible that the backfill could be designed to only send specific messages, but in practice, this can be challenging because it's not always easy to quickly identify which messages were lost. This is why idempotency is so important for downstream consumers. As just a quick review, a service is not idempotent if a duplicate request or message triggers duplicate behavior. In a service that emails users, for example, it's idempotent if it sends each distinct email only once, even if it receives duplicate messages. It's not always a problem when a backfill sends duplicate messages downstream. For example, if we run a backfill to populate a cache, that operation won't send other consumers duplicate messages, and as long as we avoid race conditions, we should be okay. So just to clarify this diagram, the topics and functions in the box are what our automation, or the automation that my team has built, provisions and maintains for our users when we set up their topics. And some of my other videos talk about, what is a pass-through function, and that can help fill in more detail about this gap here if you're not sure about it. So back to this analogy, if the stream is triggering an email for a user, for example, if the email service is not idempotent, then running a backfill would send duplicate emails to the user. Now in a more extreme case, let's say you're processing a customer transaction. Well, if that's not idempotent, you can imagine the problems that could occur. If, let's say, based on that, the customer ends up getting duplicate charges, that could be a major problem, especially if they're not even getting duplicate products sent to them, right? Now there are a number of ways to implement the backfill pattern, and we'll cover a few of these. In each of them, when we provision your topic through automation, we also set up the backfill topic. So on the administrative side, when if you want to set up a backfill topic for your tenants, you need to make sure that their token is granted a role that allows them to produce from this backfill topic, and then how you consume from that's up to you, but you need to make sure that they have permission to do that. Now you could give them a separate token for that, or it could be the same depending on your implementation. And then also, if you have dead letter topic or retry letter topic, then you have to be mindful of those same concerns about granting permission. That's assuming that you're using token-based auth. If you're using different system for auth, then you'll have to figure that out. Now, in this particular approach, this pattern here, there's an endpoint that's triggered by an HTTP action. So it's a RESTful endpoint, and it triggers an operation, a batch operation, that will bulk load the data from the data source into the backfill topic. So one benefit of this approach is that it's complete. So when the backfills run, all the data is processed. One downside is that it can be a lot of data. Now, depending on your situation, you may be able to specify, only, let's say you only want the data from the last 24 hours, or you want the data from certain products or certain things in your database. If you can, limit the amount of data that you need to pump through, that can be super helpful, especially when you only need to backfill a very small amount of data. Now, some applications require us to pause the flow of real-time data during the backfill operation, because otherwise you can end up with race conditions. So that's something you have to be careful about. Now the endpoint doesn't have to be RESTful. It could be pretty much anything that can be triggered on demand. So you could use a StackStorm job, for example, or Pulsar. It could be a Pulsar topic, or just about anything. But it's just best for it to be simple to trigger. For example, running a curl command to trigger the endpoint is about as easy as it gets. Or you could even wire it to UI and have someone click a button, which would be even easier. Now, in our case, our data engineering team is also set up to run NiFi jobs. So if you like NiFi, or I guess NiFi is kind of like Spark, um, that can be a good approach for bulk loading the data into your topic. Another option is to set up a backfill topic to consume from a Kafka source. So one downside to this approach is that it's limited to the data that Kafka retains, so it's going to be incomplete. And if you're dealing with, if you're dealing with messages that expire and you only need to process the latest messages, that can be a good option. Now this assumes that you've got retention configured on Pulsar, or on Kafka if you're running a Kafka cluster as well, and that could easily be swapped out with Pulsar. Now there are a few different ways that you could use Pulsar instead of Kafka for your backfills. This is one example. Perhaps, another example I could have put on this diagram is that you'd have the two different topics. You'd have a subscription set up that, with a pass-through function that would just be off. So it would have a subscription, it would accumulate messages, and then you would just turn on that function, and it would flow messages through into your downstream topic. Now another way you could do that is you could have a shared subscription with the retention, where the backfill pass-through is listening to messages from earliest instead of from latest, and so that way, based on your retention settings, you'd be pulling all the retained messages. Now, if you have enough storage, you could potentially retain a lot of messages. So this is another approach. Again, with this approach, because this is dealing with shared subscription, you have to be careful with possible race conditions. So you may have to pause the real-time flow while you do this, while you run this backfill. Okay, so let's talk about code. First of all, let's talk about producing a Pulsar. So for the purposes of this presentation, I'll be using examples in Java. But Pulsar also supports Python, Go, .NET, C++, Node.js, and any language that can run inside a JVM. So it supports a lot of languages. And for those of you who are new to Pulsar, producing is really simple. And this is the most basic producer. So to construct it, we provide a service URL, which is an endpoint to a Pulsar broker cluster, and then we provide a topic name. We also need to specify the type of the messages that will be produced, and in this case it's a string. Then after that, all we need to do is create messages. They're usually JSON objects, and so then we send, so after we construct that, create our message, then we call send on the producer, and that's it. It gets sent to Pulsar. It's really that simple. Now in practice, we need to deal with security. Obviously, we can't have production Pulsar clusters open to the whole world. Our case, we chose to use TLS with token auth, and this has worked out really well for us. So using token auth with TLS requires a few additional steps to set up. So first of all, you need a token, and so that can be provisioned by automation if you can get automation set up, or however you're dealing with assigning permissions. You can also do that in the command line. And then you also have to provide a trust cert. Typically that's the same cert that will be used by different users for that cluster. And then you have to enable TLS, and depending on your cluster configuration, you may need to configure some additional parameters to make things smoother for you, and that just depends on how your cluster is configured. Now there are a couple ways to produce to Pulsar. First is a synchronous producer, and it blocks while producing to Pulsar as a synchronous operation. Now you don't have to produce a string. You could produce a different type. So you could specify different type. Like in this case, we're dealing with a byte array. Now, based on our performance testing, we found that processing strings was just as performant as more complex types such as Avro. But there might be cases that we didn't evaluate that would benefit more from these other types. So if you have cases where you've gained benefit from using more complex types, I'd be curious to hear about your use cases. So by all means, please reach out to me and let's chat about that. Um, Now, Pulsar also supports an asynchronous producer. The async producer is considerably faster than the synchronous producer, but when using it, Pulsar doesn't necessarily know when your feature will complete. So if you want reliable statistics on your topics to show up, um, when we're getting stats on your Pulsar topics, and in our case, we have a UI that we built where those stats will pass through to. So yeah, if you don't wait on your futures, then it makes those stats look really strange. A new feature allows you to delay when messages are sent to Pulsar. Pulsar uses a very efficient time wheel based approach that tracks when your message needs to be sent without you needing to wait or sleep in your producer. So you can specify, hey, I want to deliver this message, in 10 minutes, and then send it, and then now it's no longer your client application's responsibility to deal with that. The broker and the bookkeeper will keep track of that and get it delivered when it needs to be delivered. And so to do that, all you need to do is specify deliver after to delay when your message is sent. And then there's another one that I think it's deliver at or something like that. I didn't mark it here. But yeah, there's one other way that you can schedule it. Now in practice, so this is an example consumer. In practice, you always want to set a timeout because theoretically it's possible that you could have your consumer deadlock if for whatever reason consumer.receive is not returning. That would mean that there's a problem with the Pulsar cluster. And so, and if you have, well, I guess a distributed deadlock would mean that Pulsar is waiting for your client, and your client's waiting for Pulsar. But yeah, in this case, like if you're just waiting forever, then it's not going to time out, even though there's a problem. So setting a timeout is actually quite simple. In this case, we're just setting a timeout of 100 milliseconds. That should be more than plenty. There should be plenty of time. If you're not getting a message in 100 milliseconds, there's something wrong. And then when you're done processing your message, you generally want to acknowledge it. Depending on if you have auto acknowledgement set on your topic, that can change things a little bit. But when you acknowledge the message, you're telling Pulsar that the message is safe to schedule for deletion. Now, if you have retention configured, then all you're doing is you're basically changing the state of the message. So now it goes into the retention period, and it'll be deleted after that retention period. If a message is never acknowledged, then it will never be deleted. So acknowledgement is very important. And then negative acknowledgement is when you want to ensure that a message is redelivered. So that's used if something goes wrong. And so when a message is negatively acknowledged, it's scheduled for redelivery, and it'll come back into the topic repeatedly until either it's acknowledged or it's sent to a dead letter topic or retry letter topic for additional processing. Now currently dead letter topics are only enabled with the shared subscription mode. I mentioned that here, right? Dead letter topics depend on message redelivery. The location in your code where you acknowledge your message is very important because once a message is acknowledged, again, as I mentioned, you're telling the broker that you can delete the message, or that the broker can delete the message. So you want to make sure, you want to be absolutely certain that you're completely done processing the message before you acknowledge it. And then, as I mentioned, if you have retention set, then that'll take effect after your message is acknowledged. Now, topics in Pulsar don't have retention by default, but you can easily configure that. But that's an administrative task. Now, when configuring your consumer to use a dead letter topic, the max redeliver count, specified right here, specifies how many times your consumer will attempt to reprocess message before it sends it to the dead letter topic. And this reprocessing happens rapidly, so if you need additional delay between your retries, then you need to set up a retry letter topic to do that. Using a dead letter topic requires your token to have adequate permission in both the main topic and the dead letter topic, so just be mindful of that. Let's see, the retry letter topic is a very new feature, and just make sure that your version of Pulsar support, if you want this feature, make sure that the version of Pulsar you're using supports it. Configuring it is pretty simple. All you need to do is enable retry, so it's specified right here, and then include the retry letter topic in your dead letter policy. And if you don't specify the dead letter topic as well, then it'll use the default name, which I showed a couple slides ago. And then you also want to specify the negative ACK redelivery delay, which specifies the delay between retries. Now, when utilizing the retry letter topic, you can also set a custom delay before your message was retried. And there may be situations where, depending on your message or the exception that's thrown, you want to change the delay. You can do that here with this consume later, or reconsume later. And then also, I should go without saying, but don't forget to close your objects when you're done with them. You certainly don't want leaking. Okay, so let's talk about batching. Batching in Pulsar allows your producer to combine messages into micro batches to increase throughput. However, it can also introduce side effects and increase latency. It's not necessary for most applications, so I usually don't recommend it unless you know that you need extra throughput at the expense of latency. Batching also doesn't work with message delay. So if you configure a message delay, your batches will be overwritten to always have a batch size of 1. A batch is considered acknowledged once all of its messages are acknowledged by a consumer. This means that if a single message in a batch is negatively acknowledged or times out, the entire batch will be redelivered. Keep in mind that this could result in duplicate messages being sent repeatedly downstream if a dead letter queue is not provided. And then if a dead letter queue is provided, since the entire batch is redelivered, it's possible for the entire batch to get sent to the dead letter queue, even if some of those messages didn't throw exceptions. So you have to be very careful with that. Now, these issues can be resolved by enabling batch index acknowledgement on the cluster, but enabling this feature does have potential memory impact. So make sure you take a careful look at memory impact if you enable that. Configuring batching on a producer is pretty simple. So you just set enable batching to true and provide the criteria for your batch. Now, if max published delay is not specified, it defaults to 10 milliseconds. So just be mindful of that. Pulsar also supports several modes of message compression. These modes can be used to reduce network bandwidth. However, on a high-performance network, it's really not necessary, and since it increases latency, I don't usually recommend it. Now, if your Pulsar client is running on a Raspberry Pi on a cellular network in the middle of the desert, on the other hand, that would be a different story. Okay, so let's cover a few best practices. So as a matter of best practice, I've mentioned this before, but I'll repeat it again. It's important to write code that can be varied by config changes. So it's very easy to do with Pulsar functions, and with producer consumers running in Docker containers, it's a little bit more involved, but it's still doable, and the benefits are worth it. Now remember that you'll accumulate back pressure if your consumer can't keep up with its incoming data stream. So you've got to make sure that your consumer can keep up. And there are cases where adding parallelism to your consumers won't speed things up, such as if they're all blocked by the same dependency upstream or downstream, if they're blocked by the same dependency that is rate limiting the requests. So if you're planning to consume from a high velocity topic, make sure you load test your consumers before putting them into production. So another best practice, you should expect to occasionally receive malformed messages. Now these wouldn't be the fault of Pulsar, they'd be the fault of whatever's producing to the topic. And a dead letter topic is a great way to handle these cases. Without a dead letter topic, a malformed message can end up throwing the same exception every time it's redelivered, and can be redelivered forever until manual intervention clears it from the backlog. You can tell I'm speaking here from experience seeing these. So, this could be a situation where the on-call data engineer gets woken up at 3 a.m. with alerts that, the code's getting tons of exceptions when really it's just repeatedly throwing exception on the same message that's stuck in the pipe. So this can be a common cause of malformed messages, or I should say a common cause of malformed messages can be from deserialization. So make sure you keep deserialization lightweight, so you're only deserializing the properties you care about. And then the most common cause of messages getting sent to dead letter topic for a lot of teams, it may not be malformed messages. In some cases, it's dealing with service dependencies, where they try calling some kind of service that is not always available. They get exceptions, and so that's another case where dead letter topic can be super useful. And there are patterns for dealing with messages going to dead letter topics. I didn't cover them here, but if you're interested in those, I'd be happy to talk more about those. As a best practice, make sure that your property names are descriptive. If they're cryptic or hard to read or like understand, if you don't, if you look at a message and it's really not clear what any of the properties are about, that's a bad practice. Especially when somebody's trying to debug a message flow and they can't make sense of the messages properties. So it's best to always use descriptive property names. Finally, if you want more information, here's some great resources that I encourage you to check out, such as Shida's Stream Native Pulsar video channel. Those videos are awesome. They cover a lot of detail in Pulsar, and including some of the newer features, and so I encourage you to check them out, especially if you want to learn more, get a kind of more of a deep dive on Pulsar and how it works. And then also I have a playlist of Pulsar videos I created, and this one will go into there. And also I'll add the Apache conference video once that's available to this playlist. And then also it's good to get involved in the community. Pulsar Slack channels is great. You can often get questions answered there and network with other Pulsar engineers and find out how they're using Pulsar. And then the mailing lists can also be useful. So if you have any questions, please reach out to me on LinkedIn or Twitter. You can see my contact information here, and I'll be happy to help in any way I can. I try and be useful, and so also if you have interests in additional video subjects, please let me know. All right, thanks so much.